Okay, so let's introduce you to organic chemistry. And before we actually start with organic chemistry, which is carbon-based primarily, and it began as a chemistry of life, let's do a review on just some of the basic chemistry concepts that we learned in the past few semesters. Okay, so let's go ahead and start our review. All right, so in terms of bonding, the types of bonds we're going to talk about will be ionic and covalent. Metallic bonds, we can discuss at another time when we talk about metals. Remember, those have to do with being involved with a sea of electrons surrounding a crystal lattice of our metal nuclei. Here, for the bonding, ionic bonds, remember, you have your cation and your anion. And ionic bonds are a charge attraction. Between our cations and anions to form neutral substances, neutral compounds. When we have covalent bonds, then the covalent bonds are basically bonds where the atoms share electrons. And they do this in order to complete their electronic configuration to get either, hold on one second. They share their electrons typically to satisfy our octet rule, although for hydrogen and helium, they only have a duet. So atoms are sharing their electrons. So let's take a look at Lewis dot structures. So in a Lewis dot structure, if we take something like lithium fluoride, let me draw a nicer lithium here. So lithium fluoride and lithium has one electron to it. Now, when we draw this, we're using Lewis dot structure. When we do this, we draw our valence electrons, our outermost electrons, as dots. Okay, so we're drawing our outermost electrons, the core electron, and basically we don't indicate. And then we have fluorine. And fluorine, being in group 7A, has 7 valence electrons. So for an ionic compound, what will happen is that this electron here is transferred to my fluorine. And when that happens, then what I get is I get my lithium ion. This. Okay. So we don't draw any dots because lithium no longer has any valence electrons. They are all core electrons. And I have my fluoride. So fluoride has its own 7 valence electrons. And it has one more that it took from my lithium. And now this has a minus charge. And it's a charge attraction from this positive and negative here and here. It's the charge attraction between plus and minus to make it neutral, and this is what we call an ionic bond. Okay, now what about covalent bonds? So if we go back to a covalent bond, so let's just take 2 instances. We'll start off with hydrogen. So hydrogen has only 1 valence electron, and this hydrogen, I'll give it a different color, has 1 valence electron. But in this case, the hydrogens can't just take, like the fluorine does, take the electron from the other atom. So how does it try to complete its electronic configuration? And we have, and energetically something that appears like a noble gas. So my blue hydrogen here will share its electron with the other atom. And because these are sharing, each hydrogen thinks it has a complete orbital. In other words, it thinks it has a 1s2 noble gas configuration. If I separate them, then basically each will have one. But right now, together, it looks like it has, each hydrogen thinks it has two electrons. We draw the shared electrons as a line. And each line indicates two electrons being shared. Okay, so what happens now with chlorine? So if I look at chlorine, chlorine has 7 valence electrons. And when we draw our Lewis dot, remember, we don't draw all in one line. We try to imagine a box around it. And then if we can, try to evenly distribute our valence electrons around it. Okay, and that's why it's 2 per side. When we share it, these two right here are going to be electrons being shared. And that's what's indicated by the single line. Chlorine on the left still has its remaining valence electrons. Chlorine on the right has its remaining valence electrons. So what do we call the valence electrons that are not shared? So these electrons are called lone pair electrons. Sometimes you'll hear us also call them as non-bonding electrons. The typical terminology you'll hear us use is calling lone pair electrons. And there are 2 of them per lone pair. So 2 lone pair electrons in a lone pair. Okay, so that's what we have. Now, if we go back to our, hold on one moment. Let me just pause here. Okay, so if we go back to our first page, we've just discussed then ionic bonds, and we have discussed covalent bonds, and we've shown how to draw them just with our valence electrons. Okay, so what we're going to do before we continue on with electronegativity, let's take a look at multiple bonds. So all I've drawn for you right now is that single bond here and here. But what happens if, to get my octet, so chlorine, because it has a 3s and 3p in its electronic configuration as its outermost shells. So what we have is what we call the octet rule. And in general, what it says is that atoms will either transfer or share electrons. So the transfer would be like your ionic bonds. The sharing electrons would be your covalent bonds. Okay. In order to achieve noble gas configuration, okay, and then in general, right? Since it doesn't apply for hydrogen, it will achieve octet. Okay, so we can see with the chlorine, I have 2, 4, 6, 8 for my blue chlorine and 2, 4, 6, 8 for my green chlorine. And so therefore, this is a good structure because it satisfies my octet rule. So let's take a look at another compound. We'll take a look at oxygen, okay? So if we look at oxygen, oxygen has 6 valence electrons. So how do we know this? Well, one of the easiest ways to determine the number of valence electrons, particularly for main group elements, is what column is it in? It says oxygen is in 6A. It has 6 valence electrons. So when it has a share, if it just shares one set of electrons, that means 2, 4, 6, 7. It only has 7 valence electrons. So it has to share another set. So if I redraw this, instead of one line, I have two because I have two sets of 2 electrons being shared. So this is the structure for oxygen, okay? And since I have 2 lines, this is called a double bond. And as you can see, if we count through our oxygens, 2, 4, 6, that's 1 dot, 6, 8, 2, 4, 6, 8, my oxygen has, each oxygen atom has 8 electrons. Nitrogen has 5 valence electrons. So if we share our electrons to try to achieve the octet rule, you see I have to share 1, 2, I have 3 sets of electrons shared in order to get my octet to 3. And I'll draw my lone pins. I'm sharing 3 sets of 2 electrons. This is called a triple bond. Okay. So now we've done our Lewis dot structures and we've talked about basically the different types of bonds that we have. Just be aware for the organic chemistry in particular, that row 1 elements, in particular, we're looking at hydrogen. We can't achieve an octet. We can only have a duet before our 1s orbital is completely full. So only 2 electrons. When we talk about row 2, it can be less than an octet. So these are like boron, okay, beryllium. But once we get from carbon onto neon, it can only do an octet. You cannot have anything expanded. So be certain when we're doing our structures that carbon through neon, row 2, basically, octet or less. And then we'll have to start talking about formal charges, okay? So in particular, row 2 will be octet or less. Anything row 3 and above, basically we want the octet. Okay, but sometimes you can have an expanded octet, but for row 3 and above, okay, so just be aware of that. But since we're talking about organic, we're going to really focus on making sure we have that octet. So let's briefly mention electronegativity. So electronegativity basically gives you an indication of the polarity So what is electronegativity? Let me give you the definition and then we'll say what it describes. So the definition is the more electronegative an atom, the greater the atom attracts the electrons in the bond. Electronegativity is a relative scale, so we usually use the Pauling scale when we talk about electronegativity. It generally goes from about 0.3 to 4.0, 4.0 being the greatest. Fluorine has an electronegativity value of 4. When you look at something like cesium, francium, those have the values of about 0.1. The trend on your periodic table, if you go left to right on the periodic table, my electronegativity increases. If you go down a column on your periodic table, then electronegativity decreases. But what we use primarily is we actually use the difference in electronegativity to determine the polarity of a bond. So electronegativity differences are always positive. Okay, and just hold on one moment. Okay, so when we determine the values, they'll always be positive. Okay, so what happens here is this. If you look at the difference in electronegativity, so from 0 to 0.4, these are non-polar covalent bonds. Okay. When you're greater than 0.4, to 2.0, these are polar covalent bonds. And anything greater than 2.0, these are ionic bonds. So why are we interested basically in bonds that have these differences in electronegativity? So if I give you a molecule, let's say methane, so carbon has an electronegativity value of 2.5. Hydrogen has an electronegativity value of 2.1. So the difference in electronegativity is equal to 0.4. So each bond, and when we talk about electronegativities, we're looking at each bond. It's not going to be the sum of my, okay. So each bond here has an electronegativity value of 0.4. And since we said 0.4 was going to be non-polar covalent, then we can say this is a non-polar molecule. Okay. So what does that mean? What that means, though, is when you look at it, it tells you how it's going to interact with different types of solvents and what's the likelihood at room temperature, 1 atmosphere, whether it's going to be a solid, liquid, or gas. When it's a nonpolar molecule, there aren't a lot of intermolecular attractions. What happens if we take a different compound? Suppose I take something like formaldehyde. When we take a look at formaldehyde, oxygen, so we have the values for carbon and hydrogen, but oxygen has a value of 3.5. So this carbon-oxygen bond right here has a change in electronegativity of 1.0. And if we draw our dipole moment, it's going to pull towards the oxygen because oxygen has a larger value. So what this means for us is that my oxygen has a slightly negative partial charge and my carbon has a slightly positive partial charge. Okay, the hydrogen and carbon, these are all nonpolar. So in this molecule, these are 0.4, so they're nonpolar. This is a polar molecule because I have nothing to cancel out this pull by the oxygen. Okay. What does that mean for us? Well, what that means for us is that now I can predict what can happen with this molecule when I'm trying to do a reaction. And I don't need dramatic or drastic conditions as we typically do for methane. So in other words, if I say, well, would I get a reaction between formaldehyde? Now let me just go ahead and add a base like hydroxide. Would a reaction occur? And if so, where is the most likely part or point at which it would occur? And since we know this is delta positive and this is delta negative, and I have a full bond negative on my hydroxide, well, we know opposite charges attract. So we know that my hydroxide would be attracted to my carbon, which is slightly positive. And because of that, it would form a bond here, and these electrons would get kicked out. So you could get collagen. You would get a product. Why would it not pull these hydrogens off? Because the hydrogens aren't slightly positive. So the only positive part of my molecule for formaldehyde is the carbon. Okay, so that's how we use it in order to predict what kind of reactions we have. So when you have an ionic compound, we just look at what's floating in solution in terms of our cation and anion. And so that's how we're going to predict it. So this is my ionic compound. Okay, so that's how we talk about bond polarity and molecular polarity. Just bear in mind, let me just go back, that the asymmetry isn't just with electronegativities. So an example for a polar molecule versus a nonpolar molecule. These have the same symmetrical geometry. They're both linear, but this has to do with the difference in my magnitude of the difference in electronegativities. If we look at basically an asymmetric geometry, and we know that the nitrogen, which is 3.0, so these are polar covalent bonds. Yeah, I'll pull towards my nitrogen. We can see that ammonia is a polar molecule. So we're looking for both the symmetry in our magnitudes, or if it's a nonpolar molecule totally, or we're looking for symmetry of structure. If it's asymmetric and you have polar bonds, then you would have a polar molecule. For nonpolar molecules, you could have it with nonpolar bonds, or if you have polar bonds in your molecule, then you have to look for symmetry in your structure. So this is actually a nonpolar molecule. Okay, so what we'll do now, talked about this, we'll take a small break, and then we'll resume again, talking about the remaining formal charges, resonance, structural formulas, and in particular, we need to go through our acid-base definitions again.